So last time we talked about how we represent the distribution of pressure down at the ground in terms of these things called surface pressure maps, which are these maps that show contours of constant values of pressure, referred to as isobars. So I thought I'd start off here by showing you an example of what one of these surface pressure maps looks like. So this is the surface map for just some day in spring. It doesn't really matter what day it is. And again, what this is showing is the distribution of pressure down at the ground, or more precisely, adjusted down to sea level, right? We adjust all of our pressure values down to sea level for the surface map over the continental US. Now, there's a lot of stuff going on this map, but for our purposes for the moment, what I want to focus on are just sort of these thinner reddish brown lines, because these are going to be our contours of constant pressure. These are going to be our isobars. In fact, if you look closely at these lines, you'll see that each of these lines has a number associated with it, and that's actually telling you the pressure along that line in millibars. So for this line here, for instance, it says 1,016. So that's saying that everywhere along this contour, pressure has the value of 1,016 millibars. The one next to it here, down here, says 1,012. So everywhere along that contour, it's 1,012. And this one here says 1,008. So that contour represents 1,008 millibars. Now, one thing you'll note from this is that every time I jump from one contour to the next, it's a 4 millibar change. So these contours are showing lines of constant pressure, and they're separated by a pressure difference of 4 millibars. Every time I jump from one contour to the next, it's a jump of 4 millibars. In this case, 1,016 up to 1,020. So then by plotting out our pressure contours like this, we can get a pretty good idea of what the pressure distribution looks like down near the ground just at a glance. In fact, to help aid our eye, every place that there's a local low pressure or local minimum in pressure, they've put in these red L's. And every place that there's a local high pressure, a local maximum, they've put in these H's. So that gives us an indication where we've got locally high pressure and locally low pressure. So on this particular day then, we see right away that the key feature was this big old region of low pressure here over sort of Oklahoma and Kansas. And so if we look at the pressure contour that's closest to the center, it says 1,000 millibars. And so the pressure inside of that is actually going to be lower than 1,000 millibars. And in fact, they've written in where the L's are, they actually have associated with that the low pressure value. So for instance, this L here has this low pressure value that's underlined of 996 millibars. And then if I start in the center of my region of low pressure and I move outwards, then I see I'm going to cross contours towards higher values of pressure. So first I hit 1,000 millibars, and then as I go northward, for instance, I hit 1,004, and then 1,008, and then 1,012, and then 1,016. So as I go outward away from my low pressure center, the pressure is increasing as I go outward. And that's true in all directions. As I go outwards, I'm crossing contours towards higher values of pressure. And then, for instance, if I go up over here, I've got a local region of high pressure. They've actually got it labeled as 1,033, and the contour that surrounds it is 1,032 millibars. And so as I go outward away from the high, I'm going to hit lower values of pressure. So this guy is going to be 1,028, 1,024, 1,020, so forth and so on. Now, the other thing to note about this is that places where the contours are close together, that's going to be places where we're going to change our pressure value very quickly as we go from one place to another. So if I start in the center of my low pressure region here, where the pressure was 996 millibars, and if I go, for instance, towards the west, I'm going to cross these contours very quickly. So every time I cross a contour, it's 4 millibars. So if I start at 1,000, then I hit 1,004, 1,008, 1,012, 1,016. So that's saying that the places where the contours are close together, the pressure is changing very rapidly from one place to another. You get rapid changes in pressure as you go from one contour value to another. Whereas places where the contours are more spread out, like around this high pressure center, that means the pressure is changing much more gradually because you're not hitting new values of pressure as quickly. So that's the surface pressure map. That's how we represent pressure distribution at the ground, or more precisely at sea level. But in a lot of cases, the really interesting stuff might not be happening down at the ground. It might actually be happening higher up in the atmosphere. So let's talk a little bit now, for the rest of this screencast, about how we represent the pressure distribution higher in the atmosphere, i.e. at upper levels. And the key player in this discussion is going to be something that's referred to as pressure surfaces. Pressure surfaces. This can be a little bit confusing because pressure surfaces sounds a whole lot like surface pressure, which is what we were just talking about, surface pressure maps, right? We're just changing the order of the words. Instead of pressure surfaces, it's surface pressure. It's kind of a Jedi mind trick. But these things are very different. When you talk surface pressure, that's the pressure down at the ground, or more precisely sea level. Surface pressure maps are sea level pressure maps. On the other hand, when we talk about pressure surfaces, that's what's going on at upper levels. Now, I should say that when we talk upper levels here, we're still talking troposphere, right? Most of the interesting weather happens in the troposphere, so we're not going to be going up in the stratosphere or mesosphere. So instead, when I say upper levels, I'm talking mid-troposphere to upper troposphere. But still, relative to the ground at least, that's upper levels. So to get started with this idea of pressure surfaces, let's first just review the notion that as we go upwards through the atmosphere, the pressure decreases with height. We know that no matter where we are, if we go upwards through the atmosphere, pressure is going to be dropping. Down near the ground or near sea level, it's more like 1,000 millibars. And as we go up, pressure decreases and decreases and decreases. So because of that, for a lot of applications, it's actually useful to talk instead about the actual geometric height above the ground. As a surrogate for height, we can often talk about pressure, because we know that the lower pressure, the lower the pressure we are, the lower the pressure level we're at, the higher we're going to be. Pressure decreases as we go upwards, so the lower the pressure is, the higher we are above the ground. So that allows us to use pressure as a surrogate for height. And in many cases, what we're going to do is talk about pressure levels, that is, places where pressure has a particular value. And there are sort of standard pressure levels that we talk about. And each of these pressure levels are going to be at different heights above the ground. So let's go through and list some of these typical pressure levels and try to give an idea about how high above the ground these pressure values would typically be found. So we're going to make a little list here of pressure levels and then their associated heights. So let's start down at 1,000 millibars. And 1,000 millibars, as we've been talking about, is roughly the sea level pressure. You'll recall the standard sea level pressure, the average sea level pressure was actually something like 1,013. So 1,000 millibars is slightly lower pressure, meaning that it's typically slightly above sea level, but it's close enough. So we can say that sea level pressures are typically around 1,000 millibars. Now, on any given day, though, that can vary a little bit. So maybe we should give it a range. We'll say maybe something like minus 0.25 kilometers, so minus a quarter of a kilometer, up to a quarter of a kilometer, say. So 1,000 millibars is down near sea level, plus or minus a quarter of a kilometer, say. Now, the next pressure level we typically talk about, actually there's a number of them, but the next one that we're going to focus on is a pressure value of 850 millibars. Now, 850 millibars obviously is lower than 1,000, which means it's going to be higher up because pressure decreases as we go up. So the next level up that we're going to talk about is 850. 850 millibars usually is found somewhere in the lower troposphere. Lower troposphere. So when we say 850 millibars, we're going to be talking low troposphere. And specifically, remembering that the troposphere has a thickness of something like 12 kilometers or so, this is going to be down around 1.5 kilometers above sea level. So this is the lower troposphere, about 1.5 kilometers above sea level. As we continue to go up, the pressure is going to drop, and the next level that we're going to focus on, in fact, we'll probably focus on this one more than any other level, is going to be 500 millibars. 500 millibars is typically going to be found about halfway up through the troposphere, more or less. So it's going to be a mid-troposphere value of pressure. It's about halfway up from the ground, from sea level, to the top of the troposphere. In terms of numbers, that's about 5 to 6 kilometers or so is typically where the 500 millibar level is going to be found. And we're going to spend a lot of time looking at 500 millibar data because 500 millibars, again, is right sort of in the middle of the troposphere. So if you're only going to look at one value, often 500 millibars can be useful because it's kind of a mid value. It's kind of the average value for the troposphere. Not really average, but sort of in the middle in terms of height. And as we continue to go up, pressure will continue to decrease. And so the next level up that we'll focus on will be 200 millibars. And that's going to be representative of the upper troposphere. Specifically, 200 millibars will typically be found somewhere in the 10.5 to 12.5 kilometer range. So again, keeping in mind the troposphere is typically somewhere around 12 kilometers deep. So this is going to be upper troposphere, 10.5 to 12.5 kilometers. So those are the 4 pressure levels that we'll focus most on. So 1,000 millibars, when you see that, think sea level. 850, think lower troposphere. 500 millibars is sort of in the mid troposphere. And 200 millibars is upper troposphere. That said, keep in mind that for each of these guys, I've shown a range of height values here. So 500 millibars is 5 to 6 kilometers. The idea being that it actually, the height at which you hit 500 millibars, although it's typically in the mid-troposphere, it actually goes up and down a little bit depending on the conditions. Some days 500 millibars is a bit higher above sea level. Some days it's a little bit lower above sea level. But it's always going to be in this mid-troposphere range, 5 to 6 kilometers or so. Okay. Now, the reason that these pressure levels, these pressure values are going to be important is because for a mixture of practical and historical reasons, when we show data at upper levels, we're typically not going to show the data at a fixed height. For instance, we're not going to show data typically at a height of 10 kilometers above sea level. Instead, we're actually going to show data at specific values of pressure. So for instance, for upper troposphere, we might actually show the data at 200 millibars, knowing that 200 millibars is usually in the upper troposphere. So to get a feel for how this works, let's say that we're interested in what's going on where the pressure is 500 millibars, sort of in the mid-troposphere. And let's say that we've got 3 observing stations here. And at each of these observing stations, we're going to measure what's going on above us. The way we do this is we release these things that move upwards through the atmosphere. They're called radiosondes. And as they move upwards through the atmosphere, they measure the pressure, temperature, density, things like that, and they relay the information back to the ground. So we get an idea of what the profile of these quantities, these physical properties, is going to look like as we go up. Now, let's suppose that at this day, on this particular location here, that we release a radiosonde from this particular observing station. And as it goes up, we know the pressure is going to drop. And it drops and it drops and it drops. And I want to keep track of where the pressure hits 500 millibars because I'm interested in what's going on at 500 millibars. So let's say above this station, the pressure drops and drops and drops, and the place where it hits 500 millibars is this X. Bang. That's where pressure was 500 millibars. This station over here does the same thing at the same time. It releases its observing radiosonde, and as it goes up, it measures pressure. Pressure is dropping, it's dropping, it's dropping, and dropping, and then bang, this X is where it hit 500 millibars. But because the conditions were a little bit different, above this station, we actually had to go a little bit higher to get to 500 millibars. And then this guy over here released its radiosonde, and it went up and up and up and up. And then the place where it hit 500 millibars was right here, bang. And again, because conditions were different at that station, it's actually lower. It's the lowest of the three. So we ended up hitting 500 millibars at different heights above sea level above each of the stations. So what if we wanted to go through and connect what's going on at each of these points where pressure is 500 millibars? That brings us to a definition. It's actually going to be the definition of the thing that we introduced at the beginning, this idea of a pressure surface. So specifically, a surface in space, a surface in space that connects all the points where the pressure was 500 millibars or any other value of pressure. So a surface in space that connects all the points with some value of pressure. In our particular case, it would be 500 millibars, but we're just connecting all the points where pressure had some value. For example, 500 millibars is referred to as a pressure surface. A pressure surface. So a pressure surface is a surface through space that connects all the points where pressure has a certain value, say 500 millibars in our case. We're going to connect all the points where pressure has a certain value. So if we go back to our little figure here, well, above each of our stations, we marked where we measured 500 millibars, where that happened. And so to get a pressure surface, that's going to be the surface that connects all of those points that have that particular value of pressure. So we're going to go through and connect all of our points. And because we were connecting points that had a pressure of 500 millibars in this case, this is going to be our 500 millibar pressure surface. Now, at this point, you're probably figuring that this is basically the same thing as an isobar, or pressure contour. And it is a very similar idea. We're connecting all of the points that have the same value of pressure. But there is a notable difference. And that notable difference is that you're going to have to start thinking in 3D at this point. Because we're not just going to be looking at cross-sections like we've done here in this figure. You have to keep in mind that in addition to this cross-section, there's also going to be points that are out of the screen a little bit towards you or into the screen a little bit, and you're going to have to do the same thing at those points. So for instance, you could imagine running around your room, sending up radiosondes through your room, pretending that the pressure drops quite a bit in your room, so pretending it's the atmosphere. And then every time that pressure drops to a certain value, you mark that point in space, in 3 dimensions. And then you go to another spot in your room, and you measure the pressure upwards until it drops to that same value of pressure, and you mark that. And then do that another point in your room, and you're going to end up with a whole bunch of dots at certain positions in height above your measuring spots throughout your room. And each of those dots is going to be where you hit your specific value of pressure. And then you have to connect them all. And the way you're going to connect them all, so now this is 3D, is by like putting a tent that connects all of them. So it's like having a tent that extends over the floor that connects all of these points where you hit that certain value of pressure. I'll have some figures here later on that sort of try to illustrate that basic idea of sort of envisioning this in 3 dimensions. So here's a simple example from the textbook. This is just showing sort of a thin slice of one of these surfaces. And so here's the ground down here. And again, the idea is going to be that at every point along the ground, we're going to measure pressure as we go upwards. And then we're going to record where the pressure hits 500 millibars. And then we pick another point and we do the same thing. And then we pick another point and we go upwards until we hit 500 millibars. And another point, we go upward until we hit 500 millibars. And so we're going to get a bunch of dots extending above the ground, marking places where pressure was 500 millibars. And then we're going to connect them all. And we're going to connect them all with a surface kind of like a tent that extends above the ground, connecting all of these points where pressure was 500 millibars. That's going to be our 500 millibar surface. And that's represented by this gray thing here. It's a very simple structure in this particular case, but you get an idea of how it sort of has this three-dimensional feel to it. Just a little foreshadowing, you can see in this particular figure, places where the temperature was warmer, we actually had to go a little bit higher to reach this 500 millibar level. And places where the temperature was colder, we didn't have to go quite as high to hit 500 millibars. And that's going to be a general rule. Typically places where it's warm in the lower troposphere, your pressure levels are going to be higher above the ground. And typically where it's cold, you're going to hit those levels a little closer to the ground. And so as a result, our pressure surfaces that connect all of those levels are going to be higher in some places and lower in others. Now, as I mentioned earlier, one of the reasons that we're interested, one of the reasons these things are important, is because when we look at data at upper levels, we're actually not going to look at data at a given value of height. We're not going to look at data, say, at 5 kilometers above sea level. Instead, we're going to look at the data at a given value of pressure. If, for instance, we might be interested in the data where pressure is 500 millibars, which means we're going to end up showing data as represented on these pressure surfaces, because these are the places where pressure has a given value, and we're going to show the data at that value of pressure, which means we're showing data on this surface. So the maps that we make when we show the data at these given values of pressure, these things are called upper level charts. Upper level charts are maps that are showing data on one of these pressure surfaces. And in a lot of ways, upper level charts are going to be similar to the surface pressure charts, surface pressure maps we looked at earlier, in the sense that we're going to be showing contours that represent constant value of certain things. But there is one big difference between our upper level charts and our surface maps. So if you remember back to the surface maps, the things that we're plotting constant value of are pressure, right? We're plotting contours that represent certain values of pressure, isobars. So for instance, in the map that we looked at earlier, we had a contour that represented 1,000 millibars, and then the next one was 1,004 millibars, and then 1,008, and so forth and so on. And by doing so, we were then able to map out what the distribution of pressure looked like at sea level. Well, on our upper level surfaces, that's not going to work, because if you remember, an upper level surface, by definition, was a surface that connected points with the same value of pressure. For instance, in this case, 500 millibars. So everywhere along this surface, pressure has the value of 500 millibars. And so it's not going to work to plot isobars then, because there are no contours, right? Everywhere along the surface, the value of pressure is the same. So the surface itself is a contour. I mean, you can't plot contours when the pressure always has the same value. So that's going to be a big difference. We're not going to plot contours of constant pressure on our upper level charts. Instead, what we're going to do is we're going to end up plotting contours of something, but instead of pressure, those contours are going to represent the height of the surface above the ground. That's what we're going to plot contours of. Keeping in mind, again, that some places 500 millibars was higher above the ground. Some places it was a little bit lower. And it's kind of like a tent extending. Some places it's higher, some places it's lower. And so the contours that we're going to plot on our map are actually going to be representing the height of the surface above the ground, above sea level to be precise. So instead of plotting pressure on our upper level charts, the contours on the plot show the height of a pressure surface above sea level. So height of the pressure surface above the ground, or to be precise, above sea level, to be more precise. So when we plot our data on our upper level charts, instead of plotting isobars, the contours are going to represent how high that surface was above the ground at that point. That's what we're going to be showing. So over here on the right, I've got a simple schematic upper level chart then, sort of giving you a feel for how this works. So this is the 500 millibar chart, 500 millibar pressure surface. So it's kind of representing this thing that we were just looking at earlier, this guy here. And so again, we're showing east is to the right, north is upwards. So we're looking down from above. We're looking at the horizontal distribution. And what each of these contours is showing is how high that surface was above sea level along that contour. So for instance, down here in the southeast, this contour here shows that the surface in this particular case was 5.6 kilometers above sea level. And then as I go towards the northwest, the next contour says that it was 5.5 kilometers above sea level along that contour. And if I keep going, 5.4, so it's a little bit closer to the ground, not quite as high. And then 5.3, again, dropped a little bit, and so forth and so on. And so by looking at this, by plotting out the heights, we can get a feel for kind of what the geometry, or more precisely the topology, of this surface looks like. Or down here to the southeast, the surface was higher above the ground. And as I go up here towards the northwest, I'm dropping down towards lower heights, which means I'm going downhill. The surface is slanting downwards towards the northwest in this case. So in a lot of ways, this is kind of like reading a topo map. For those of you guys who have done hiking or orienteering, scouting, that kind of stuff, at some point along the line, you probably had to read topographic maps. Topographic maps are basically this. They're maps that are showing elevation of the ground above sea level. So each of the contours on the map represents the elevation of the ground above sea level. Well, this is basically the same thing, except it's showing elevation of our pressure surface above sea level. So we can see where the pressure surface was higher above sea level, and we can also see where it drops down to be closer to sea level. Okay, this is actually what I just said. So upper level maps kind of read like topo charts, where the contours represent height of the pressure surface above sea level. So to get a feel for how this works maybe in 3 dimensions, let's kind of look at this from 2 perspectives. So up here on the right, I've got our schematic upper level chart. It's the same chart as before. So again, this is showing data north upwards, east to the right. And so we're looking down from above, and each of these contours is showing height of the surface above the ground. And let's see if we can imagine what this would look like if we were to do a cross section through this and look at it from the side. So specifically, let's take a cross section along this line here, along the dotted line there, extending between 2 points, one to the south, one to the north. And for reference, I'm going to go ahead and label these points. The one to the south, I'm going to say is point A, and the one to the north, I'm going to call A prime. And in fact, let's suppose that we have 2 observing stations along this cross section as well. Let's say we've got one observing station down here to the south. It actually happens to be below this point where it was 5.6 kilometers, this contour here. That's an observing station at the ground. And then we've got another observing station up here along the contour that says 5.3 kilometers. And I'll label those as well. So we'll say that one of them is B and the other is C. Now what I want to do is sort of see if I can imagine what this thing would look like, what this surface, this upper level surface, this 500 millibar surface would look like if instead of viewing it down from above, we look at it from the side. That is, I want to take a cross section, a vertical cross section running from A to A prime and look at it from the side. And that's what we're doing down here in this figure down at the bottom. This is a cross section, and we're looking, this is the ground down at the bottom, and height above the ground here going upwards. And so we're looking at this now from the side, which is sort of the typical way we look at the world. And each of these data points here is representing one of the points along our line, A, B, C, or A prime here. And it's representing the 500 millibar surface for each of those points. So each one of these dots down here represents one of these dots along the dotted line, and the X's are the position of the 500 millibar pressure level above that point, going upwards. But I haven't labeled them. You'll notice that I did not label the points down at the bottom. So is it running from A to A prime, or is it running from A prime to A? Which way are we looking at this? Is the left-hand side going to be A running to A prime, or is it going to be A prime running to A? Which way is it going to be? We should be able to figure this out, right? It looks like maybe we can't figure this out, but we probably should be able to figure it out because we have our upper level chart here. And what our upper level chart tells us is how high the pressure level was above sea level. So for instance, along this line here, it's telling us that our pressure level was 5.6 kilometers above sea level. And as I go northward, it's getting lower, getting closer to sea level. So what that's telling me then is the surface is typically higher above sea level down here to the south and then drops off as I go towards the north. So if I look at my cross section from the side, the places where I've got my 500 millibar level being higher above sea level, over here to the left, that must correspond to A. Whereas up here, where the 500 millibar level was closer to the ground, 5.3, that's got to be the north side. That's got to be A prime, right? So this is saying places where we hit 500 millibars higher above the ground, that had to correspond to the A side, and places where we hit it closer to the ground, that had to correspond to the A prime side. And the 2 points in between, those must be B and C then, with B towards the southern side where the heights are higher and C towards the northern side where the heights are a bit lower. So then if we go in and we label our axes over here, we must then have north pointing towards the right because we're going from higher to lower. So it's northward towards the right. As we go northward along the line, the heights drop, and then height above the ground is upwards here. Okay, we can actually go a step further here because we actually have two of the stations that happen to be right on these contours. So we actually know how high above the ground the pressure surface was for those two stations. So if we draw in these two stations B and C here, well, station B happened to be right on this contour that says 5.6 kilometers here, which is telling us that the pressure level is located 5.6 kilometers above sea level. That's how high it was above sea level. And C happens to be on this contour up here, which says 5.3 kilometers. And so what that's telling us is that at that point, the 500 millibar level was 5.3 kilometers above sea level. And so then if we go and we connect all these points here, that's going to be our 500 millibar surface as viewed from the side. So this gives us an idea of how to translate back and forth. So the upper level chart is the view looking from above. And then if we were looking from a cross section, like down here, the chart would tell us in this case that the upper level surface, the 500 millibar surface, is higher to the south and falls offward towards the north. So in our cross section, here on the south side, on A, it's higher, and then it falls off towards the north. So that's how we kind of translate this guy into different perspectives. So you can get a feel now that for this part of the course, and actually for most of the rest of the course, we're going to have to start thinking about things in 3 dimensions. We're going to have to start thinking, trying to visualize the data and from different perspectives in 3 dimensions. Okay, so here's an attempt to sort of represent what this would look like schematically in 3D. So this isn't an actual pressure surface, this is just data that I made up. But it sort of gives you an idea of how to visualize this in 3 dimensions. So it's a 3D perspective. We've got south to our left, north to our right. So you can pretend, for instance, that you've got Houston to your left, Chicago to your right. And if you've got Houston to your left and Chicago to your right, you must be looking which direction? Towards the west. So into the screen is towards the west here. And so again, the basic idea is that every point in this space along the ground, you would go upward and measure pressure, and it's dropping, and it's dropping, and it's dropping, and you record where pressure hits 500 millibars, say. And then you do another point, and it's dropping, and it hits 500 millibars. And you do another point, and so forth and so on. And then you connect all of those points where you hit 500 millibars, and that's your 500 millibar pressure surface. And what I'm trying to show, what I'm representing along this surface, are contours of constant height above sea level. So each of these contours is representing height above sea level along this surface. So along this contour, the surface has the same height above sea level. Along this contour, same, so forth and so on. Now, just looking at this geometrically, you can see that the highest heights are going to be here generally to the south. And as I go towards the north, I'm going downhill a little bit. So I end up with lower heights here towards the north. And you can see that in the contours as well. As I go towards the north, I cross contours towards lower heights, lower heights, lower heights, until I end up with lower heights here in the north. There's also a little dip as I go towards the west, right here in the center. So I cross another contour, and my lowest heights are actually right here in the center, here in this little dip. And then it comes back up a little bit. So that's kind of what the 3D topology of this surface looks like. It's actually highest in these corners here in the south, and as you cross the contours, you're going downhill, and my lowest heights are here in the center where this little dip is. Now, what would this look like if I translate it into an upper level chart? So to translate this guy into an upper level chart, all I really have to do is imagine looking at it from above and then plotting out the contours. So that's what I'm going to do on the next slide. I'm going to translate this into an upper level chart in terms of the contours of height. And I'm going to put south along the bottom and north along the top. So you can visualize a little bit what this is going to look like. And it's going to look like this. So I've got south along the bottom, north along the top. And these are my contours of constant height above sea level. I haven't labeled them, but we know that the lower heights were to the north. So generally we're going downhill this way. And if you go back to the previous slide, so we had our highest heights in the corners, we go downhill towards the north, and the lowest heights were actually here in the center. Translating that into an upper level chart, our highest heights are in the corner, we cross contours going downhill towards the north, and our lowest heights were actually here in the center. We cross contours again. This is a little dip. This is the lowest point. We come back up, and then we go back up towards higher heights to this corner. So that's how we translated that 3D perspective into an upper level chart, just where the contours here are going to give us an idea of what the geometry of this surface looks like in 3D, where it's higher and where it's lower. Here's a real example. So this is a upper level chart. Again, I'm showing the 500 millibar chart here. So we focused a lot on 500 millibars. And the black lines on this chart are our height contours showing height above sea level. You can see there's a bunch of them. They're going to be a little bit hard to read for you guys, probably, but I can read them, probably. So for instance, this guy here, this contour says 582, which really means 5.82 kilometers. So that's 5.82 kilometers above sea level. Next one up, 5.76. Next one up, 5.70, 5.64, so forth and so on. So we're going towards lower values. We're going towards lower heights. So generally, we're higher above sea level down here, and as we go towards the north, we're going downhill. We're going towards lower heights. In fact, by the time I get all the way up here, we're talking 5.16. This next one's going to be 5.10. So we've dropped down from 5.8 down here all the way down to 5.1. So we're going downhill as we go towards the north. So again, the height contours are giving us an indication of what this surface looks like, what its topology is in 3 dimensions. One thing I should probably point out about this is that for all the examples that I've shown, both the real case and the schematics, I put the higher heights to the south, and generally the lower heights were to the north. And that's almost always going to be the case, to within some minor variations. But generally speaking, you're going to find higher heights to the south, and as you go towards the north, the surface is going to slope downwards. Now, there may be places where it's distorted, like here, where it's actually sloping left to right. But generally speaking, as you go towards the north, you're going to be sloping downwards. Your surface is going to be going downhill in most cases. And we'll see why that is here. Maybe tomorrow. Most likely tomorrow. Okay, so that's what our upper level charts look like and how we interpret them. Now there's one last point to make about this, which is translating this data about the heights into information about pressure. So to set the context here, let's think back to our surface pressure maps, our sea level pressure maps. When we did a sea level map, we were actually plotting directly contours of pressure. And that allowed us to look at a glance and see where pressure is higher and pressure is lower, generally speaking. And that's going to turn out to be really useful when we start thinking about circulations, because those pressure differences are going to be what's going to drive our winds, drive our circulations. Now, when we look at an upper level chart, we're not plotting contours of pressure. We're actually plotting contours of height. But I'm going to make an argument here that it's almost the same thing. That is, we can actually interpret our contours of height on our upper level charts in almost the same way that we interpret our isobars on a sea level pressure map. So to see how this works, the first thing to keep in mind is that when we're comparing pressures from one place to another to see where pressure's higher and pressure's lower, we actually need to compare pressure at the same height above sea level. We know that pressure generally drops when we go upwards, and so it's not fair to compare pressure at different heights. If you want to compare pressures, you really want to pick the same height above sea level, and that'll give you an idea of generally where it's higher and generally where it's lower, because it's a fair comparison. So let's go ahead and do that. So we've got a little schematic over here, and this is showing a view from the side, a cross section, and we've got the ground down here, and this red line is my 500 millibar pressure surface. So everywhere along that line, pressure has a value of 500 millibars by definition. And I want to go and compare pressures to see where pressure's higher and lower generally. So I need to do that at the same height above sea level. So let's draw in a contour with a given height above sea level. So here's a little line that shows fixed height above sea level. And I'm going to label it A on one side and B on the other, just to make it easy for reference. And so given that this guy is the same height above the ground everywhere, it's fair to compare pressure values. It's a fair comparison. And so generally speaking, I want to know where along this line does pressure have a higher value and where along this line does pressure have a lower value. Now, you might think that we can't figure this out, but in fact we can. We have enough information here on this figure to figure this out, because remember that the red line was a pressure surface, the 500 millibar pressure surface, which means by definition, everywhere along the red line, pressure is 500 millibars. That's how we define that surface. We also know that if we pick any point and we go upwards, pressure is going to drop. And if we pick a point and we go downwards, pressure is going to get bigger. Which means that anytime we start along the red line and go downwards, we're starting at 500 and going towards higher values. So everywhere below the red line then has a pressure greater than 500 millibars. Pressure greater than 500 millibars. Whereas if we start at the red line and we go upwards, pressure is going to drop. And so everywhere above the red line, pressure is less than 500 millibars. All right, so red line is 500. If we go downwards, it's bigger than 500. If we go upwards from the red line, it's less than 500. Well, if we think about our horizontal line now, over here at A, this guy A, this point is actually below our 500 millibar surface, which means the pressure over here is bigger than 500 millibars. If we go to the other side, point B is above the 500 millibar surface over here, which means its pressure is less than 500 millibars. Which means that we can actually infer directly from the information in the figure that the pressure at point A has to be bigger than the pressure at point B. Pressure at point A is greater than the pressure at point B. And this is actually going to be a general argument, because any time that you have a pressure surface that is higher in some places and lower in others, you can actually draw a fixed height, a horizontal line, kind of like we did here. And what you'll find is that along that horizontal line, where it's fair to compare pressures, wherever your pressure surface was extended upwards above the ground, pressures along your horizontal line will be bigger. And wherever your pressure surface dipped downwards along your horizontal line, pressures will be lower. So if we're looking along horizontal lines like this, again, to make it fair to compare the pressures, generally speaking, places where your pressure surfaces are upwards at higher heights have higher pressures along this line, and places where the pressure surface dips down translate to lower pressures along this line. So people sometimes get a little bit confused by this because, we know pressure decreases as we go upwards. So you would think, well, higher heights must mean lower pressure, right? But that's not actually what we're doing here. Remember, we're talking about higher heights of our pressure surface. And when the pressure surface is higher above sea level, the points along the horizontal line have higher pressure. And when your pressure surface is lower down, the points along the horizontal line have lower pressure. So we can translate information about the height of our pressure surface directly into information about pressure on a horizontal line. So as a result then, when we're looking at our upper level charts, the height above sea level is going to end up playing the same role as the pressure on our surface maps. That is, for the most part, you can think of higher heights of your pressure surface as being equivalent to higher pressures. You can think of your higher heights on your pressure surface as being equivalent to higher pressures, and lower heights on your pressure surface as being equivalent to lower pressures. So when we're looking at upper level chart, places where we have higher heights of the surface translate into higher pressures, places that have lower heights translate into lower pressures. So it's kind of the same information that we are getting on our sea level pressure map. Now I'm going to reinforce this point just a second. I've already said this, but I want to reinforce it because people often find this confusing. Again, we're not talking about higher heights, pressure decreases as you go upwards. We're talking about the same pressure surface. So everywhere along that surface, pressure has the same value, say 500 millibars. But when that surface is found higher above sea level than along your horizontal line, that's going to translate into high pressure. And when the surface is lower, closer to sea level, than along your horizontal line, that's going to translate into lower pressure. So we're taking information about height on the pressure surface and translating it into pressure along a horizontal line at fixed height. And when you do that, you find that places where you have higher heights translate into higher pressure, places where you have lower heights of the surface translate into lower pressure. And so it kind of plays the same role as the isobars did when looking at a sea level pressure map. Okay, so we'll see this idea again moving forward. So I'm going to leave it here for now. And with the next screencast, we'll actually start talking about different kinds of patterns that we see at upper levels and at the ground.